I found the picture of the smelliest sofa that I could on the internet because this is about code smells and about an acronym that we think might help you remember some kind of baselines about how to write beautiful code, SOFA, which I'll explain in a moment. But the theme of this whole discussion about refactoring and about design patterns, which is what we're talking about this week and next, are things that kind of go hand in hand. And as we mentioned at the very, very start of the semester, writing code that's correct is only part of the challenge. The sort of bigger challenge in many cases is writing code that's maintainable, that somebody else coming to your code can relatively quickly start getting a grasp of how it works. So that makes us ask the question, how do we know what makes a piece of software easy to maintain, or aesthetically, if you will, what makes it beautiful? Like, what kind of guidelines are there? Is it just something that's subjective, or can you quantify it? And if you can quantify it, do the quantitative measurements actually stack up? Do they accord with what seasoned programmers would say? This is a beautiful piece of code, would also be a piece of code that scores well on any quantitative metrics. And what tools can we use to support helping to identify those things? So we'll start with the qualitative. If anybody's heard the term code smell, a code smell is something that brings to your attention that something might be wrong. It's just like a real smell, right? A real smell that smells weird doesn't necessarily mean something is wrong, but it means you should pay attention because something could be wrong. And this is where we kind of came up with this acronym that will capture 4 symptoms that we think are sort of the root causes of a lot of different code smells. There are dozens of code smells, and we're going to show a few examples in the code that I'll show momentarily. But a lot of the code smells boil down to the fact that you have violated one or more of the following 4 things. With respect to a particular method, right, a function call, a method that you write, let us ask the following 4 questions about it. Is the method short? How short? Well, you should, the rule of thumb, according to Martin Fowler, is first you should make your method as short as you can, and then make it shorter than that. So there's always room to make your method more concise. A one-line method is not necessarily too short if that line captures intent of the thing the method's doing, which, by the way, means a good method should do one thing. And you can see how those go together, right? A long method is not likely to be doing just one thing, and a method that only does one thing shouldn't need to be very long. Does it have few arguments? There's a number of reasons why having fewer arguments is better, and we'll talk about those. And does the mechanism stick to a consistent level of abstraction? And again, we'll give an example, but basically what that means is a method should either say what is to be done, or it should say how to do certain things, but it generally shouldn't mix them. So we'll give an example that will make it more obvious. There is a tool, as you might imagine, that finds code smells. In the Rails world, it's called Reek. However, you don't usually have to run it separately because all of the techniques we're going to talk about today, and many others besides, are things that Code Climate does for you. And it sort of computes a weighted average of how you're doing on a lot of these different metrics, and that's what your GPA for a file is based on. So what do I mean by a single level of abstraction? I'll explain it, but then I'll show you an example. And I think once I show the example in code, it'll be a lot easier to understand. If you're trying to do a complex task, you need to divide and conquer the task, right? You don't write a single long function that does a lot of things. Instead, you have helper methods of various kinds around the function. And if you, I don't know if anybody ever took a class in writing where they tell you that a good news story is sort of hierarchically structured, that the first paragraph of the news story is like the high order bits, the who, what, when, where, and how, and then the details are in the paragraphs after that. So that if all you read is the top paragraph, you understand what the story is about to tell you, but you don't know the details. If you're interested in specific details, then you can continue reading and look for the specific paragraphs that illuminate them. So in the news story analogy, each paragraph sort of deals with a topic and goes into detail about that topic. But if all you read is the top-level summary, at least you get what the key idea is. So we'll talk about an example of what it means to apply that to code. Lots of arguments. Why is there a guideline that a function or a method should have few arguments? Well, for one thing, it's hard to get good test coverage, right? If different combinations of arguments have different effects, There's a lot of paths through the code that could be influenced by that, and we'll actually show a metric that computes that quantitatively. It's also hard to stub or mock while you're testing because you have to have values for all of those arguments, right? The function is only doing one thing. You only need to test one thing, but you need to pass it a full set of arguments. So you've got to come up with some values to pass around. If any of the arguments are Boolean, that's almost always a yellow flag. If you have an argument that's Boolean, and the way that that argument is used is that it basically gets the function to do one thing or another thing, depending on if it's true or false, probably there should be two functions. And somewhere else, maybe there's a function that dispatches to one or the other. Right? So you can sort of get rid of Boolean arguments for free. And if you have arguments that always seem to travel around together, you might need to extract a class. For example, if you've got a handful of functions that deal with manipulating postal addresses, and you find that you're always passing around a street, a city, a state, a zip code, really, you probably should define a new class that captures the concept of an address, define some methods on that class, and then pass around a single instance of that class as one argument to functions that want to consume it. So if you see that you have kind of the same set of arguments that are being passed around to a number of different methods, that's a flag that you might want to extract those things into their own class and define things around them. Quantitatively, what can you measure? There's a couple of metrics that are actually really good proxies for if methods are too complex or not. One of the ones that works really well for short functions is called ABC complexity, which stands for assignment branch condition. Literally, all it does is it computes the L2 norm, which is the square root of the sum of squares, of the number of assignments, the number of branches, and the number of condition statements in a function. That's it. The National Institute of Standards and Technology, or NIST, very exciting organization. Among other things, they set standards for government contract work and software. They actually have a guideline that code written for the government should have an ABC score of less than or equal to 20 for any given function. A function that scores larger than that should be broken down into subfunctions. And we'll show an example in a minute, like I said, of how to do that. Again, there is a gem that checks your ABC complexity, but you don't usually need to use it separately because Code Climate will report this if you go in and look at the stats for individual files. The other quantitative thing you can compute is called cyclomatic complexity, which is basically just the number of linearly independent paths that you can take through a piece of code. So in this hypothetical piece of code, I've shown a function that has a while loop, and then it's got a conditional here. The while loop can have a path where you go straight through it. It can have a path where you go one or more times around the loop body. The if can either pass through the false branch of the conditional or the true branch of the conditional. So the way you compute this is it's the simple formula, the number of edges minus the number of nodes, and twice the number of connected components. Don't worry about memorizing the formula. If we ever care, we'll give it to you. But basically, if you apply it to this, you get 3. There are 3 linearly independent paths you can take through this code. And NIST has also said that, yes, there's an upper bound on 10 per module or collection of related functions is a reasonable max. Again, there's a tool that calculates it, but you almost never need to because Code Climate will call you on this if it turns out that your complexity is too high. So let me quickly summarize the smells and metrics that we've seen so far, and then I'll show you a live example, which actually makes this, I think, easier to understand. Static metrics, the code to test ratio, and test coverage, we talked about those things. Those are quantitative measures that tell you something about how good your testing is. We've looked at 2 different ways to calculate the complexity of a piece of software, the complexity of a function. And basically, the goal of having multiple metrics is you don't use any single metric as a pass or no pass, but you look for places in the code where multiple metrics are being violated. And usually the metrics actually tend to travel in packs. If a piece of code manifests a problem with respect to one of these metrics, probably it's going to manifest problems with one or more other metrics as well. So you tend to think of it kind of like test coverage, right? It's not as if you say, well, if my test coverage is not at least exactly 90%, then I don't have enough test coverage. Instead, you're using these to identify places where improvement might be needed. As an example of applying these to some real code, here's kind of a convoluted function that someone wrote as a solution to a homework assignment at one point. The idea is that you have a bag of a list of words, and you want to find all the words that are anagrams of each other. But with a little care, you can whittle the function down to that, and it does the same thing. And the reason is that the person on the right understood that if you look in the Ruby standard library, you can find this thing called group by that actually lets you take a list and partition it into sublists depending on the result of another predicate function. So if you actually evaluate these against flog, not surprisingly, flog score is a lot lower. It's not just that there's fewer lines of code or fewer tokens. It's that the control flow is a lot easier to understand. Right? Like the version on the right does not have nested conditional. This version's got 2 nested loops and a conditional inside the nested loop. It manipulates a separate assignment of this temp array. So by knowing the language's idioms, you can often get your code quite compact and in a way that someone who knows the language well can read it pretty quickly. So flog is not, like any other metric, it's not something authoritative, but it's a place to go to draw your eye to where there might exist some problems. And remembering that a recommended upper limit, according to the NIST standard, is a flog score of 10 is about the maximum. Obviously, this should have been split into multiple functions. So let me go through and do a code example of how this might work, because I think a live example of refactoring will help bring this home a little more readily. There's also things like if you have a loop, a for loop iterating over an array. Remember way back when we started looking at Ruby, it's got all of these map-like collection methods that make your code a lot more concise. There's things like replacing a method with an object. If you've got a method call that does a specific thing, and that thing is pretty complicated, consider pulling that responsibility out into a class. Now, just like we did in the convert example, the top level method of that class is going to be very short, but it's going to have a bunch of little helper methods that can all be tested separately. If you have a long list of parameters, we said parameters that travel around in a herd or in a clump, sometimes you can extract a class and put all those parameters together. Now you're just passing a single class object around. 2 code smells called shotgun surgery and inappropriate intimacy. Inappropriate intimacy means there's a method in class A that knows a whole lot about the implementation of something in class B. That's why it's inappropriate intimacy. And it makes you ask whether one of those methods is really in the wrong place. If method A really, or if the method in class A really knows so much about what's going on in class B, why is that method in class A to begin with? Maybe it should be moved into class B and exported in some way that class A can use. We'll see a couple of examples of that when we talk about design patterns. Too many comments. Trivial comments are not useful, but comments that go out of their way to explain what's going on in a method can often be eliminated if that method is so simple that it almost explains itself. And the way to achieve that is to pull the intermediate code out into other methods. Each method by itself has a descriptive name, including the names of its variables, and does one thing with few arguments, a single level of abstraction. It's not a whole lot to take in all at once. So if you find yourself extensively commenting, it's because the code's too hard to understand. The solution is not to have more comments, it's to make the code simpler. Guilty for, most of the time if you have a long method, it probably is not sticking to a single level of abstraction. So extracting methods and classes in the way that we did in this example, which is admittedly a fairly simple example, but the recipes in red will actually take you quite a long way. So wrapping up the idea of the different kinds of characterization tests in this intro to refactoring, the goal of characterization tests is to let you add test coverage so that you can protect yourself before you start making changes. The way that you do that is you get the app to reveal its behavior, whether it's at the integration level or at the level of individual classes or methods. You capture what you observe. Now you have a repeatable test that if anything ever changes, you're going to know about it. We love Code Climate because before Code Climate, you sort of had to run a lot of these different metrics manually on your code if you cared about them. What I like about Code Climate is that it sort of runs a whole bunch of things and it computes a reasonable weighted average and kind of draws your attention to places where things are really bad. So it will warn you if your methods are too long, if you've got deeply nested conditionals, if you have variable names that are useless because they're one letter long. I mean, storage is free, so give your variables good names. They will warn you about duplicated code. You've got 2 or 3 functions where a bunch of code is almost identical across those functions. Maybe there's an opportunity to pull out that code into a helper and call the helper from different places. Refactorings. This lecture gave just a very, very kind of simple example of how to think about refactoring. There's more examples that go into some depth in the textbook, but really, if you're going to be doing some work in a language, having a refactoring book that has examples in that language is super, super useful. The canonical book is the Martin Fowler book on refactoring, but editions of it have been published that are tailored to all different languages. And the reason those are useful is that different languages have different idioms that make the different kinds of refactoring easier. So it is well worth investing in a copy of this book for any languages that you're going to spend serious time in. At each step, what have we done? When you extract a method, you have exposed a seam. You have exposed a place where you can separately test or modify by stubbing out the behavior of the app without further changing the source code. So part of the goal here is now you can test at those newly exposed seams, and you can test pieces in isolation. And then in the higher level test, you can stub those out. So again, you're separating the behavior of what's under test from all the things that it relies on. That's what when we started doing unit testing with RSpec, that was the basic approach. And at every point, you're trying to improve the structure of the code, and we have both quantitative and qualitative ways to do that without changing the correctness of the code, and that's what your tests capture, right? If the tests are passing and they're decently written, then the code's doing the right thing. So it doesn't mean that you will have less code, but it means that any given chunk of code that has to be comprehended as a unit is going to be smaller. You're going to be doing a lot of refactoring, so it becomes pretty fun after a while. I hope you get used to it. For now, we will close off this topic, and we will pick up on Thursday with applying the same kind of thinking to the design of classes. I'll see you then.